We have three, as I mentioned, three very, very useful talks, very relevant talks. So I'm going to turn it over to Suzanne to talk to us about the subsea desalination. You can now share your screens, Suzanne, and start your presentation.
Thank you all for having us and listening to us and for giving us the opportunity to work with you. As Ram said, I'm Suzanne Chess, and I'm Managing Director and Spokesperson for Tiabzu. Also here with us are some of my team members, Dr. Tim Forstman, Dr. Dan Tormey, who you've heard a bit from, who's with Catalyst Environmental Solutions, our regulatory advisors. Mike Edwards and Bob Evans will be presenting with me, and Ryan Elliott, our subsea engineer, will be joining shortly. That brings us to Tiabzu, which brings the tools, technology, and techniques to change the environment for desalination. It leverages natural processes of deep ocean hydrostatic pressure for reverse osmosis, relative density between freshwater and saline seawater for buoyancy control, and a symbiosis with existing offshore infrastructure to make subsea desalination competitive. 40% of the energy required for coastal desalination is for multi-pump pre-osmosis. This can be reduced, if not eliminated, by operating below ocean's most biologically productive zones. And this also removes the environmental impact of intake and discharge accumulation on phytoplankton, the marine carbon cycle, potential negative feedback on climate that disruption of these systems can cause. This is expected to confer regulatory advantages for pilot and post-pilot scaling.
We embarked on Tiabzu, desalination by reverse osmosis system within a submersible hull. Key components of the desalination module are its membrane system, RO water receiving tank, umbilical, membrane flush, and extraction pumps. The umbilical connects the system to a surface supply vessel, platform, or shore. The umbilical holds power, communication cables, and a snorkel connecting an RO water receiving tank to the surface. This maintains the tank's internal atmospheric pressure. The difference between it and the ambient seawater keeps water flowing through the RO membranes. A pump extracts purified water from the tank to the surface or shore, or with a switch of a valve into a bladder.
This is Mike Edwards. You might think of the Tiabzu system like a hot air balloon. Instead of using difference in air temperature for lift, its balloon or bladder that you see on top there provides lift using the approximate 3% difference in relative density between the RO water and ambient saline seawater. This integrated buoyancy system facilitates implementation. Tiabzu models can deploy using A-frame or davit. They can also launch from commonly accessible harbor ramps and small tow vessels. The bladder is used for buoyancy control for deployment and for recovery or maintenance or at end of life. During mobile operations, buoyancy is used to drop into position and to maintain at operational depths. This buoyancy system integration is expected to significantly lower capital costs associated with implementation and address the regulatory requirement for removal at end of equipment life. The RO maintenance cycle is 5 years with a 25-year life. In an alternative configuration, the bladder can be filled with enough RO water to be employed to lift objects subsea. Water is non-compressible, more stable, and safer than using airbags that accelerate toward the surface or sink in response to changes in depth and ambient pressure. Heavy lift cranes generally used for subsea deployment and removal projects are in limited supply. They have very high day rate. So competition for these cranes with a myriad of offshore projects requiring their use can cause significant delays, which raises capital expenses. With respect to needing a heavy lift crane to deploy and recover a large desal system, it's enough to tip the scale outside of economic viability. To put in perspective the significance of penciling down prospective costs of implementation, The price for a barrel of crude or equivalent natural gas is probably between $24 and $70 a barrel. Water is less than a penny per gallon for most markets, so it converts to about 42 cents a gallon, or about 42 cents a barrel. There are other variables that offset some of this, such as throughput volume and the non-depleting resource in seawater. We approach repurposing of offshore infrastructure as a collaborative process, working together with owner-operators, leveraging their assets while, without interfering, they continue to operate. This collaboration establishes a framework for development and regulation before momentum for decommissioning takes over. The alternative use provides a transition as productivity depletes, and in the case of Tiabzu, as alternative energy sources come online. It's a transformation that is supportive of a new offshore economy.
If any of you are traveling through Santa Barbara, please have a look at our Marine Megatropolis exhibit that has been up for 2.5 years in the main terminal. It's very relevant. And on behalf of our team, I thank you.
Awesome. That was perfect. I would like to see a few of the RPC members and my own picture at the bottom there where it says you.